Hello everyone. Let's continue our discussion on deriving the load curves for PMOS and NMOS. So we are done with step one, where we have converted all the node voltages, let's say VGS, with the gate to source voltage of your PMOS as a function of V, and this is how it looks like. The next step is to convert the VDSP as a function of output voltage, because that's the voltage that we are left with. So we will be converting the VDSP as a function of output voltage. So we have something as output voltage, we have something as input voltage, and we have the common drain current. So we will be getting the load curve or of a PMOS in that step. So the next step is to convert your VDSP into a function of output voltage, and that's pretty simple. If you just try to carefully look into this particular equation, your V out is VDSP plus VDD. So you just need to add your VDD to the VDSP, and you can basically convert this complete curve into a function of V out. So let's do that very slowly. So we'll move these curves to the left. Next step is to convert this whole curve, the x-axis of VDSP as a function of V out. So we'll write down that equation using V out equal to VDD plus VDSP. It's just a shift of VDD towards the left hand side, and you get V out equal to VDD plus VDSP. Okay, so now what if you carefully look into this equation, it says that if your VDSP is, let's say, negative 2 volts, let's say we'll take the extreme ones. If your VDSP is negative 2 volts, you add a positive 2 volts to it, you get your V out. So when your VDSP is negative 2 volts, your V out is 0. And if your V out is 0, you lie somewhere at this point. Okay, now once your V out is 0 and let's say your V in is 1.5, you see some finite value of current at this point of time. For example, let's say VDSP was again negative 2 volts, VDD was positive 2 volts, your V out is 0, and let's say your gate voltage, the V in, is 1.5. So at V out equal to 0, you see a finite current flowing. And that the reason is pretty simple. The reason is the output when you say V out equal to 0, it basically says that the output capacitor is completely discharged and we need to charge the capacitor. So that this is the charging current of your capacitor. So let's try to draw the curve and explain it even in a better way. So we have shifted this complete curve by a value of positive VDD. So for example, if your VDSP is 0, you just add VDD to the VDSP and your V out becomes 2 volts. So your V out becomes 2 volts. So same current that you see at VDSP equal to 0, you will see a same amount of current when V out equal to at V out equal to 2 volts. And the reason is, so over here if you see at V out equal to 2 volts, the current is 0. And that makes sense because whenever your V out is 2 volts, it says that your output capacitor is completely charged and there is no flow of current, that there is no charging current that's flowing to the output capacitor. That's why there is zero current, and as a result of that, you see at output voltage equal to 0, you see exactly zero current, no matter what is the value of input. And this is true only when PMOS is in combination with NMOS to form a CMOS inverter. Okay, in that case we are talking about these curves, not as a PMOS as an independent device. Things becomes a bit different when PMOS is taken out of the CMOS inverter and analyzed independently. So we're not talking about that situation. We're talking about a situation where PMOS is clubbed with NMOS to form a CMOS inverter. Okay, so this is the case. Whenever so we'll take one more example. For example, let's say your your V out is 0 volts. Okay, whenever V out is 0 volts and we obtained V out equal to 0 volts at this value, so whenever your negative VDSP is negative 2, the highest, the maximum fullest potential attained by your drain voltage. So if your negative VDSP is 2 volts, if a negative VDSP is 2 volts, if you just add positive 2 volts to the equation, your output voltage becomes 0. Okay, so your V out becomes 0, and at every gate voltage of V in, you will see a finite amount of current whenever your V out is 0. And the reason is, whenever your output voltage is 0, it means that your output capacitance is completely discharged and you need to charge that. So this is the charging current of it. Okay, so and let's say we'll take another example. When your VDSP is 1 volts, let's say negative 1 volts, your V out becomes positive 1 volts, which means if when we say it's positive 1 volts, it means it's half charged and it needs some amount of current to get charged, and this is the value of current. Okay, so this is how to look into this curve. So the curves, when it is looked from a from a PMOS point of view, it's a bit different, but you need to give a different angle to the curves when you try to look it from a CMOS inverter point of view, and this is the angle that we are talking about. So once we are done with the conversion of these graphs as a function of V in and V out and IDSN, we call it as a load curve. This is what we call it as a load curve for PMOS transistor. Now everything is a function of V in and V out, and there is no dependency on VGSP or VDSP or even IDSP. So this is unique. You have unique IDSN, you have V out voltage, you have V in voltage. The next step is to do the same thing for your NMOS transistor, and then we will be kind of on the same page. So your PMOS and NMOS will be on the same page. You'll have a curve for PMOS which looks something like this as a function of V in and V out. We will have a curve for NMOS which we'll be deriving in some time from now. That will also be a function of V in and V out. The next step is to just merge it and get the CMOS voltage transfer characteristics. Okay, so let's do step by step. The step 3 in this one is to obtain the load curve for NMOS transistor using above equations, using these equations. Okay, so the load curve for NMOS becomes pretty simple because your VGSN, if you evaluate VGSN, is V in minus VSS, and your VSS is nothing but your ground potential, so your VGSN is directly V in. Okay, so it's very simple. It's not complicated as you see in the case of VGSP. It's very simple. VGSN is V in and VDSN is V out. Okay, so the curves for the deriving the load curves for NMOS becomes pretty simple because of the nature of the equations. And the reason for this one is that NMOS is placed at the bottom. So it's as good as you're analyzing an independent NMOS, and your drain node was connected to V out, which is varying. Your gate was connected to V in, which is again varying, but your source is connected to ground. This is in contrary to PMOS, which has got a different node potential for source and drain. So the things becomes complicated for PMOS, but in this case, in case of an NMOS, your VGSN is directly equal to V in, your VDSN is directly equal to V out. So the deriving the load curves for NMOS transistor becomes pretty simple, and I'll show you how. So we'll use the below graph. So this is the graph that we had derived. We had done the spice simulations also for this kind of graphs. So you have IDSN over here, you have VDSN, and you have VGSN. The next step is to convert these two to a function of input and output voltage, and it's very simple. You just need to convert all your VGSN. You need to replace all your VGSNs over here to V in. You need to replace all your VDSN to V out, and that's it. You will be getting the NMOS load curve. It becomes pretty simple over here. Okay, so if you see, if you do by a step-by-step process, VGSN is equal to V in. So whatever you see as value of VGSN, those will be exactly the value of V in, and VDSN will be exactly as V out. So just replace. It's just a matter of replacing the names here. So you take this curve, you change the names. So the next step is to, so this will be called as the load curve for NMOS. The next step is to take these two load curves. We'll remove the equations that is not needed. So we'll take these two load curves. We'll take this NMOS, we'll take this CMOS inverter, and we'll try to get the voltage transfer characteristics. The final step is to get the voltage transfer characteristics of this particular CMOS inverter. So it's pretty simple. Now we have everything as a function of V in and V out. It's just a matter of merging these two curves in the right fashion. Okay, so that will take an amount of time. So what we'll do, we'll take these two curves, merge it, and derive the voltage transfer characteristics for CMOS inverter. So let's try to do all this in the next video. Thank you.